Welcome to the General Chemistry 1 class. This section is on the electronic structure of atoms, focusing on the quantum numbers part 1. In this lesson, we will describe the electronic structure of atoms in terms of main energy levels, sublevels, and orbitals and relate this to energy. The wave function. The solution for the Schrödinger equation is a wave function, which is a function of the coordinates describing the location of the electron in three-dimensional space. Wave function is conventionally expressed in another coordinate system called the spherical coordinate system, in which the position of a point is expressed in terms of the distance of the point from the origin, r, and angles theta and phi. Radial and angular functions. The wave function of psi is a product of two functions called the radial function capital R and the angular function capital Y. The radial function represents the electron density or the probability of finding an electron at a given distance from the nucleus R. On the other hand, the angular function, which is a function of angles theta and phi, depicts the shape of the orbital and its orientation in three-dimensional space. Every radial and angular functions represent a set of numbers called the quantum numbers. These numbers can give one information about the energy and orbital in which a certain electron occupies, as well as the electron's behavior. There are four quantum numbers, and these are number 1, principal quantum number, or small letter n, number 2, angular momentum quantum number, or small letter L, number 3, magnetic quantum number, or small letter m with the subscript of L, and number 4, electron spin quantum number, or small letter m with a subscript of S. The first three quantum numbers will be the focus of this discussion. Principal quantum number. The principal quantum number, or small letter n, is the quantum number that describes the energy level of an electron, as well as the size of the atom. The permissible values are the counting numbers such as 1, 2, 3, and so on. An electron with higher principal quantum energy corresponds to greater distance of the electron from the nucleus and consequently greater or less negative energy, as the electron has lesser attractive force with the nucleus and implies larger atomic size. Angular momentum quantum number. Angular momentum quantum number, or azimuthal quantum number, or L, which can be any whole number from the quantity of 0, 1, 2, 3, and so on. For every value of n, the allowable values for L are from 0 to n minus 1. Naming atomic orbitals. The angular momentum quantum number describes the shape of the orbital. Each L value has a corresponding letter designation. The L values 0, 1, 2, 3, 4 have letter designations S, P, D, and F. The letter designations S, P, D, and F originated from the description of emission lines of certain elements, that is S from sharp, P from principal, D from diffuse, and F from fundamental. Letter designations for higher L values are in alphabetical order next to F, skipping I and letters used in the preceding L values. An atomic orbital is named using n value and the letter corresponding to the L value. Examples are shown on the right. An electron shell refers to the energy level in which an orbital or a group of orbitals belong. The table on the right shows the uppercase letters corresponding to each energy levels as shown on the right. On the other hand, electron subshells are atomic orbitals belonging to the same shell. For instance, 3s, 3p, and 3d are subshells of the capital letter M shell, or n equals 3. Note that each shell with a principal quantum number n has n subshells. Magnetic quantum number, or m subscript of L, corresponds to the orientation of an atomic orbital in three-dimensional space. A given value of L has m subscript of L values which are integers from negative L to positive L. The number of m subscript of L values in a given value of L tells the number of orbitals in a subshell. These orbitals are of the same energy, hence called degenerate orbitals. Consider the orbitals under the third energy level, or n is equals to 3. The 3s subshell has only one m subscript of L value, implying that there is one s orbital in this subshell. For the 3p subshell, there are 3 m subscript of L values corresponding to 3 degenerate p orbitals, while 3p subshell, there are 5 m subscript of L values corresponding to 5 degenerate d orbitals. Example number 1. Identify the permissible values of L and m subscript of L for n is equals to 4 state. Solution. The permissible values of L must be whole numbers from 0 to n minus 1. Since n is equals to 4, the possible values of L are 0, 1, 2, and 3. For each value of L, the possible values of ML are integers from negative L to L. Hence, the permissible m subscript of L values for each L value are summarized in the given table. Example number 2. How many orbitals are there in the 4f subshell? Solution. For a subshell with a given value of L, there are 2L plus 1 orbitals. For the 4f subshell with L is equals to 3, the number of orbitals is given by number of orbitals is equals to 2 times 3 plus 1 is equals to 7 orbitals. Example number 3. How many orbitals are there in the fourth energy level? Solution. For a given amount of n, the total number of orbitals is n squared. Hence, if n is equals to 4, the number of orbitals in this energy level is given by number of orbitals equals 4 squared is equals to 16 orbitals. Electrons can be found at any distance away from the nucleus. Hence, orbitals technically extends through infinity. However, atomic orbitals acquire shapes that correspond to at least 90% chance of finding the electron in a certain region in space. The shape of orbitals can be obtained by graphing the square of the angular function y squared. The s orbital are spherical in shape. The s orbitals of different energy levels differ by the number of spherical regions within the orbital in which electron has no chance to be found, called the radial nodes. By looking at the radial probability distribution plots for the 1s, 2s, and 3s orbitals, we can see that the radial nodes corresponds to the distances with zero radial probability. The radial nodes are spherical regions in which the wave function starts to change its sign. Referring to the illustration on the left, radial nodes are the white regions while difference in color refer to difference in signs. As the principal quantum number increases, so does the number of radial nodes. For any orbital, the number of radial nodes is affected by the subshell it belongs. Number of radial nodes is equals to n minus L minus 1. From this equation, we can see that 1s orbital has no radial node, 2s orbital has one radial node, and 3s orbital has two radial nodes. P orbitals. The p orbitals are dumbbell-shaped orbitals passing through either of the three axes, x, y, and z. The three degenerate p orbitals are named as px, py, and pz. Each of the two px and two py orbitals correspond to either m subscript of L is equals to 1 or negative 1, while 2pz orbital corresponds to m subscript of L is equals to 0. The lowest n value that can have L equals 1 is the second energy level, or n equals 2. Hence, possible p orbitals are 2p, 3p, 4p, and so on. The p orbitals have at least one planar region where the sign of the wave function changes sign, and the chance that the electron lies herein is 0. This is called the angular node. As for the case of 2p orbitals, the angular node is found at the center, suggesting that electrons in p orbitals stay more likely away from the nucleus. The number of angular nodes does not depend on the principal quantum number, but on the angular momentum quantum number. For any orbital, the number of angular nodes is given by number of angular nodes is equals to 1. D orbitals. The d orbitals consist of 5 degenerate orbitals: dxy, dyz, dxz, dx squared y squared, and dz squared. For the 3d orbitals, 4 out of 5 orbitals have the same shape, while the other one resembles that of the 2pz orbital, but with a torus or donut shaped lobe lying on the xy plane. For the 3D subshell, 3dxy and 3dx squared y squared correspond to m subscript of L is equals to 2 or negative 2. The 3dyz and 3dxz are corresponding to m subscript of L is equals to 1 or negative 1, while the 3dz squared orbital corresponds to m subscript of L is equals to 0. Just like p orbitals, there is zero probability that an electron in any d orbital can be found at the center, as some of its angular nodes pass through this point. To summarize, the 4 quantum numbers are the principal quantum number n, angular momentum quantum number L, magnetic quantum number m subscript of L, and the spin quantum number m subscript of S. The first 3 quantum numbers describe the energy level of the electron and the shape and orientation of the orbital it occupies. This is the bibliography or references. Thank you for listening.